Hello again, and this is our second abstract algebra video lecture. This time, still in that first section of chapter 0, but we'll be looking at some of the definitions. These definitions actually start before the first proof we did in the first video, but we didn't need them for that proof, so I just went ahead and put them off. We're going to go over this, do some examples. This will probably be a short video. The next one on this section will be on the Euclidean algorithm and how to use it and how to apply it to the other theorem that we have in this chapter. But for this point, I just want to go through these definitions. Traditionally, if I have a normal semester, I have quizzes on definitions where you have to state them. And I'm not exactly sure if I'm going to be able to do anything like that this semester. My guess is probably not, but if I do figure out a way, I will let you know. If I do, it'll probably be some sort of quiz where you'll be able to repeat it as many times as you want until you get it right. The only reason I'm thinking about still doing it is because the whole reason I do it in the first place isn't because memorizing is the most important thing, but it is a way to make sure you know these definitions, and knowing the definitions is the first step in using them in proofs. That's the idea. Anyway, let's get on to the definitions. One thing about these definitions is they are pretty much what you would expect them to be, and one important thing about that is these definitions, as we have them here, are describing things that you're already familiar with, in some cases back to middle school or grade school. So these aren't going to be hard definitions to understand, but part of the point of this section is making sure you understand why we define things the way we do and how we take our knowledge of what things actually mean in practice and putting those in a precise way in which we can use it later in proofs to prove more complicated results. So that's the reason for this. In any event, let's go ahead and start off by looking at divisibility. I'm going to zoom in as much as I can here for divisibility. There. Okay. So what we're going to look at first is divisibility right here. Oh, and I do have to make one minor adjustment here, so let's do that. Where is it? Where is it? Right here. Let's fix that while I got it ready here. I think that's the only, that's the only greater than or equal to sign I need to adjust. Okay, so first thing we're going to talk about is divisibility. Now, the idea of divisibility is we're going to be talking about two integers and saying whether one is divisible by another. And this is a term that we have lots of terms for in math. We say one number is divisible by another number, but we can also say that that number is a multiple of the second number, or the second number is a factor of the first number. So these are all ways we write this same thing. So A is divisible by B. We also translate that as B divides A. That's probably the only terminology that you wouldn't have heard earlier than a college class. B is a factor of A, or, as we see here, A is a multiple of B. Any of these descriptions here are ways to say the same thing. And essentially, this is the idea is the same sort of thing we're used to, where we're talking about one number being some multiple of another. In other words, one number being the second number repeatedly added to itself. That's one way to put it. But let's actually take a look at an example of what we mean by that. First, as a simple example, so for multiples, let's Let's put that in text. Okay, so multiple. An example, and if this were in class, I'd be asking you for these examples, but an example of a multiple here would be, we would say, for instance, 180. Hang on. I think I need to zoom in a little bit more here to get this to work right. 180 is a multiple of 12. That's going to be our example that we're going to look at. Now, this is something that you're used to seeing in past classes. This isn't anything unusual for you. 180 is a multiple of 12. You're probably used to phrasing this as 12 divides evenly into 180. And that's a fine way to talk about it. But in this class, we're rarely going to use division in the sense of we're rarely going to use division for definitions of things because division has some problems, as we saw last time with the division algorithm. When you actually start talking about division, there are cases where you have remainders, and to avoid that issue, we refer to all these things in terms of multiplication. So let's take a look at what we mean here by multiple. We can say 180 is a multiple of 12. We could also phrase this as the same thing, 12, or 12 is, I think I need to zoom in again a little bit, factor of 180. Or, in other words, 12 divides 180. Okay, so those are some, sorry about that, some examples of what we've got here. 180 is a multiple of 12. 12 is a factor of 180. 12 divides 180. We also use this little notation up here. You can see B vertical bar A. That means essentially B divides A. That's the way we phrase that. Okay, so let's go back in here and see what our definition tells us about this. We say A is divisible by B. In other words, 180 is divisible by 12 if there's some integer C such that that first integer is the second integer times that new integer. In other words, what I would be looking for in order to say 180 is a multiple of 12, I would be looking for, and I think I'll put this one in red, 180 equals 12 times some number. We don't know what that is. Well, you probably already know what that is, but if you don't, you can figure it out real quick, and I'll probably have you pause this to figure that out. But this is what we mean by something being a multiple. We mean that that first number here, the 180, if it's a multiple of 12, it's equal to 12 times some other number. So go ahead and pause this for a second, figure out what that number is, make sure I'm not messing with you here or whatever, and then unpause it, and you can come back and see what that is. Okay, and if you're back, this should have been pretty easy for everybody. 180 is 12 times 15. Now, here, that number happens to be 15. It doesn't matter what that number is. You'll notice we don't even specifically say anything about C. C can be any number. So by this, by default, a couple things wind up being true. Every number is divisible by 1, and 0 is divisible by every number other than 0. So those are a couple of statements we could put here as, okay, so don't need bold there. Every, no, sorry. A lot of times I'll say number, I mean integer, pretty much always in this class. We don't get to the point where we're talking about things that aren't integers. Every integer is a multiple of 1. And 0 is a multiple of every integer. And zoom back out. Let's see if I might be able to stretch that out. I can't quite, but there we go. That's pretty close. All right, so every integer is a multiple of 1. 0 is a multiple of every integer. That's all we mean by a multiple. You can come up with lots of examples of this. This is also something I'm sure you're all familiar with, have seen it a lot of times, but this is what we mean by a multiple. Our second definition is a little bit more complicated, but not too much. It's the GCD, or greatest common divisor. And again, this is something you will have seen before when you're dealing with numbers, fractions, that sort of thing, way back as far as grade school. I mean, although fractions, typically you're not exactly looking for the greatest common divisor when you're adding them, but there are situations where you need them. But here, for greatest common divisor, essentially we're looking for two things. And let me go ahead and start off here by getting no, I'll use the highlighter. So we have two integers, and we say that they are not both 0. What that means here, we do have to be a little bit careful about this, that means one of them or the other can be 0, but not both of them. So in other words, we're allowed to have one of these two be 0, but we're not allowed to have both of them be 0. And we say that if we get a positive integer that satisfies these two conditions that we'll get to, we call it the greatest common divisor of A and B, or we abbreviate that GCD of A and B, like GCD parentheses A comma B. And we have two conditions for this. And you can almost guess what they're going to be by the name of the definition. We're calling this the greatest common divisor, right? Greatest common divisor. So we need a couple things here. We need this to be a divisor. In order for it to be a common divisor, it has to be a divisor of both A and B. And so that makes it a common divisor. And then we want to force it to be the greatest of those. In other words, any other divisor of A and B has to be smaller than the greatest. And with that in mind, you get two things that go into this definition, and you know what they're going to be. First, it has to be a common divisor. So, for it to be a common divisor, we need D to divide both A and B. That's what it means to be. First of all, D dividing A means D is a divisor of A. D dividing B means D is a divisor of B. And if it divides both, that makes it common, a common divisor. So that's the first part, this common divisor here that we got. The second part is that we want it to be the greatest common divisor. And how we do that, we pick some other divisor. So here we pick some other integer which divides both of them. So this is essentially, let me zoom in so I can write a little bit clearer. I have to zoom in because if I don't zoom in, the writing gets sloppy. I'm using my finger here. So this integer C is itself a common divisor. That means C, in order to be a common divisor, has to divide both A and B. So C is a second common divisor. We already know that this integer D that we were interested in the first place has to be a common divisor, so it has to divide A and B. Here we're looking for a second one, also a common divisor, and in order for D to be the greatest, it has to be bigger than or equal to any other divisor. In other words, here I've picked some other divisor. D has to be bigger than that. That's what it means to be a greatest common divisor. So we got all of that. So hopefully that makes sense. Let's actually look at a quick example. And here we're just going to look at an example that you can pretty much do in your head. I mean, I haven't picked it out yet, but I'm not going to pick out a hard one. We will have a way in the next video to actually figure out GCDs for numbers that you can't just immediately look at and figure out in your head what they are. But for right now, we are going to look at a slightly easier one than you might guess. I would normally ask you all to come up with one, but you know, that's a little bit hard on the YouTubes or the whatnots. Okay, so there we go. Oops, that is not what I wanted. There we go. Okay, so we're going to look at a GCD now. I'm probably going to have to, in fact, let's move that down a little bit. Yeah, there we go. Okay, so let's actually look at, let me pick two numbers here. Let's say here what? I need to zoom in again. Find the GCD of, let's pick two here. Let's say 42 and 120. Okay, so these are the two numbers I'm interested in here. So I want you all, and I'm going to give you a chance to do this on your own. You're going to pause this and figure out what this GCD is. Let me put the numbers in here. No, do them in red again. 42, 120 equals blank. Okay, now there are a couple ways you can do this. Honestly, the easiest way, although when I'm describing this, doesn't sound easy because it's vague, is what you want to do is just look at these and figure out what their divisors are, figure out what prime divisors they have in common, sort of combine those, multiply all the prime divisors that they have in common, and get it that way. And you can do that without even like listing them out or anything. You can just sort of figure it out in your head as long as the numbers are small enough, which in this case they should be. So that's not something you can't do. But there is sort of a more brute force way to do it, and that's without the algorithm we're going to get to next time, which is just list all of the divisors of each of these numbers. So list out all the divisors of 42, list out all the divisors of 120, find the biggest one that appears in both lists. Like I said, it's brute force. My advisor used to call these kind of methods brute force and ignorance, but it's a brute force method. You can do it. It still is only good for small numbers that are relatively easy to factor, but you can do it that way, or you can just look at them and see, okay, what goes into 42 that also goes into 120, and you can sort of do it in your head that way. Anyway, go ahead and pause the video, figure this out. You can list them out if you want, or you can just figure out what number goes into both of these and sort of doesn't have anything left over. And when you're done, go ahead and restart, and I will finish this off for you. Okay, so you should be back. What you should find at this point is the GCD is, if I've done this correctly in my head, which I'm pretty sure I have, because these numbers aren't too big, the GCD should be 6. Now, let's actually list these out just to sort of do it out by hand. So if I have 42, and I'm looking at my divisors, there aren't too many here. 120 is a little bit worse, but there aren't too many at 42. 1 obviously is a divisor of everything, and because of that, we'll see a lot of times 1 is going to one will automatically be a common divisor for everything. Doesn't have to be the greatest, but it will be a common divisor. 2 also clearly goes into 42 because 42 is even. It's a little bit, it might not automatically be something you would know, but it's not too hard to figure out. 3 goes into 42. Here, a quick way to tell if 3 goes into a number is add up the digits, and if the sum you get, if that's a multiple of 3, so was the original number. So 1, 2, 3, and then we get the ones that you normally think of with 42, which are things that multiply together to give you 42, which in this case is, let me zoom in again, 6 and 7. Also at this point we would get what? 14, 21, and 42. One other thing you can note when you list these out is they should pretty much go in pairs. Unless the number's a perfect square, you should have the first one and the last one multiply together to give you the number. So 1 times 42 should give you 42. 2 times 21 should give you 42. 3 times 14. 6 times 7. Those each pair gives you 42. If the number's a perfect square, there's going to be an odd number of these, and the one in the middle multiplies by itself to give you the number. That's not our example here, though. Okay, next is 120. Let's look at the divisors there. Divisors. Again, we are going to start with, let me zoom in again. 120, doesn't matter, we still start with 1, 2, 3. In this case, 4 still goes into 120. Also, 5 goes into 120. 6 goes into 120. And at this point, we're able to start getting numbers that we can, or we're close to being able to get numbers where we can see what their product is. I think we still have 10 before we can do that. Then 12. I don't think I'm missing anything. It's possible that I am. I'll check after I'm done with it, though. 5 times... 5 times 24, 4 times 30, 3 times 40, and what's next? 2 times 60, and then finally 1 times 120, and that should be our list. Okay. So here, this should be our list of divisors. I'm pretty positive I didn't miss anything. 7 doesn't go into that. 3 only goes into it once. We don't have any other primes to worry about, so yeah, at that point we should be good. So this is our list now. Now, what we're looking for to find the GCD, and again, like I said, this is the hard version, or the brute force and ignorance method. Here, the biggest number that's in both of these lists is 6. That means that is the GCD. Okay, and that's all there is to it. You don't have to do this out with a list. You can do these, if the numbers are small enough, you can do them in your head. And if you can't do them in your head, the algorithm we're going to get to next time is the way you do it. Okay, so that's our next example. Does that make sense? Hopefully that makes sense to everybody. I'd normally ask you, but as I said, that is hard to get a response on the YouTubes. All right, so next up we have prime numbers. Again, this is something you should be familiar with. Here, our actual definition that I've already written out is the one you should be familiar with. We say a number's prime if its only divisors are 1 in itself. Here, we phrase this a little bit more carefully. We say its only positive divisors are 1 in itself, because we do allow negative numbers to be considered as divisors. And here, we also, you'll notice, make the point that the number that we're looking at has to be bigger than 1. Here, technically, if we didn't have that in, 1 and the number 1 would also be divisible by 1 in itself. So it would be considered a prime under that idea. And while that is fine according to that word definition, it does make things that we need to describe how the integers behave a little bit, it makes them not work if we include 1 as a prime. And our definition for composite is actually fairly easy. Essentially, every number that's not prime is called composite. So every integer bigger than 1 that isn't prime is composite. So we don't have to talk about different factors or anything like that to talk about composites. We just have to say it's not prime. And I'm just going to list out some examples. Maybe I'll try and list, I don't know, I don't know how many primes. Not too many, though. Okay, so the smallest prime and the only even prime is 2. The next prime is 3. Next one is 5. Next one is 7. You'll notice I'm skipping some here. 1 we already talked about isn't prime. 4 is 2 times 2, so it's got a factor other than itself, which means it's not prime. 6 is 2 times 3, so it's not prime. I'm not going to go through every example like that. Our next prime is 11. Next one's 13. Next is 17. Next is 19. Next is 23. Then 29. Then 31. Then 37. Then 41. 43. 47. And I think I'll stop there. That's good enough. That's all the primes less than 50. I'm not asking you to memorize all the primes less than 50 or anything, but you should have a pretty good idea about what are some primes, at least some small primes. The first 30 primes go up to 113, so that's not an unreasonable number to know, but there are infinitely many, and we will prove that. So you can't memorize them all. But small ones, it's probably worth knowing some. Okay, so these, let me write this out. All primes less than 50. There we go. Okay. Sometimes it's easier to write than others. All right. So all primes less than 50, these are the ones we get. Nothing special about that stopping at 50. You can stop at 100. You can stop wherever you want, but no matter how far you go, there are always more primes. So there are infinitely many primes, and we will prove that, but not today. The next thing, and maybe the last one I do, although I might put another one in just to have it there, which is the least common multiple, which is related to what I've already got. But the next thing is what we call numbers who are relatively prime. And that means that we have two integers whose GCD, let's get this here, integers whose GCD is 1. So we call those relatively prime. In other words, they don't have any factors in common with each other than 1. That's the idea. So, again, you could come up with lots of different examples for this. Let me have you pause the video and come up with 3 pairs of numbers who are relatively prime to one another. And these can be anything, and you might come up with a quick way to make a bunch of them, and that's fine, but we'll look at some different examples. So pause, come up with 3 pairs of relatively prime integers. So one pair, both of which are relatively prime, a second, and then a third. Okay, if you're back, I will guess I'm not going to guess which ones you came up with, because they would be, who knows what they would be. But the first pair that you might have come up with would be maybe 2 and 3. The reason that I say that would be easy is we already have primes up here. Primes, by the way we've defined them already, are something that they automatically don't have any factors in common because their only factors are 1 in themselves. So if they're different, their only common factor is 1. So 2 and 3 is an example of a pair of relatively prime numbers. In other words, if I want to do this, GCD of 2 and 3 equals 1. That's essentially what we mean by a pair of numbers being relatively prime. Now, I'm going to come up with 2 more pairs. You can always pick any pair of prime numbers, and those will automatically be relatively prime as long as they're not the same. But I'm going to pick some that are different. So here, like for instance, if I were to pick 6 and 10, those wouldn't work, right? Because they have a factor of 2 in common. But for instance, if I pick 6 and something without a 2 or a 3, say 35. 6 and 35 are relatively prime because their GCD, let's do this again, GCD of 6 and 35 equals also 1. Okay, so that's another example. And let's come up with another one. Let's say 20. So you'll notice that, that number only has factors of 2 and 5. So whatever else I pick should be something that doesn't have any factors of 2 and 5 in order to be relatively prime to it. So let's say we pick something with only factors of 3, but because we want to pretend we're being interesting, we'll not just make it 3 itself. We'll make it 3 to the third, or 27. So those are 3 different examples of integers that are relatively prime. Okay, so hopefully that makes sense to everybody. Let's actually see if I can do the last bit here, which is going to go, if I can do it here, Okay, don't need bold. Okay. I'm going to put one new definition down here. And because it's similar to the GCD definition, you might almost already guess what it is. It's the least common multiple. I'm not going to call it D this time, I'm going to call it M. It's the least common multiple. If it satisfies, it's going to satisfy two statements again. Hang on. Well, okay, I'm going to have to type this out, I guess. So here, if I want a least common multiple, first it has to be a common multiple of A and B. In other words, both A and B have to be, M has to be a divisor of both A and B. In other words, both A and B are divisible by M. And we have one other one. Oh, hang on. Let me do it this way. Star. Okay. So that makes it a common divisor, like we saw before. And the second thing is we want it to be the least, or M is a common multiple, sorry. We want it to be the least common multiple, so we pick some common multiple. So if N is positive integer satisfying for which, I'll put it this way, for which I messed that up. Hang on, let's fix this here. So I don't need both A and B to be divisible by N. I need both A and B divide M. For which, and down here, for which A and B divide N. Then, so that means N is a common multiple. Since M is the least, we should be able to say M is less than or equal to, okay, hang on. M should be less than or equal to N. All right, let me put in the equal to here because I have to do that by hand because they wouldn't spring for that symbol when they were doing this. Okay, so let's do that down here. Okay, hang on. Okay. Oh, and I need to edit this here again, don't I? I've got to be a little bit careful here. Okay. I think I've changed everything there. I copied some stuff, so hopefully it's all fixed now. Let's see. For integers A and B, not both 0, we say that the positive integer M is the least common multiple of A and B, or phrase it LCM of A and B, if it is let me put the highlights in again. If it is first a common multiple, in other words, A and B both divide it, and then it is the least, in other words, it is smaller than any other one. And we could do a quick example of this. Let me actually do that here. We're doing this in blue. hang on. Let's put... okay. All right, so let's do a quick example. Here, if I pick two numbers, hang on. If I pick two numbers, let's pick the ones I was talking about before, 6 and 10. We could list out multiples like we listed out divisors before. Now, the problem there is there are an infinite number of multiples, but you only have to get to the first one that they share in common. But I'm not going to actually make you all do that version. I just want you to think through this here. Let's put these in, 6 and 10. So again, pause this for a second, figure out what the least common multiple of 6 and 10 is. It might be helpful to you to factor them first to figure out what you would have to be a multiple of both of them. So go ahead and pause and come back when you're done. Okay, everybody should be done now if pausing works the way I think it does. And so here, what we actually should find is our LCM is 30. And maybe I actually will write out the list of multiples. It's pretty quick to do. So if I write out multiples of 6, I would write out here 6, 12, 18, 24, 30, 36, 42, and so on. Keeps going on forever. Doesn't matter. You don't have to write them all out. And it's a good thing because you couldn't. And let's look at multiples of 10. And here we would start off with 10. It's 10 times 1, 20, 10 times 2, 30, 10 times 3. At that point, we could even stop. I'm going to write a few more, but 40, that didn't work out so well. 50, and so on. Hang on. That's not what I want to do. Okay, anyway. So here we have the multiples of 6 and the multiples of 10. You will notice that the first number that appears on both lists is 30. And it does have to be the first in order to be the least common multiple. Hang on, try not to get quite so much of it there. Okay, so the least common multiple is the earliest number that appears on both lists. There we go. Okay, and that is how you can find an LCM of a pair of numbers pretty quickly. All right, I think that's good for today. This is a list of definitions. Most of these are things you should be familiar with, at least as concepts, but the technical definitions are worth knowing. And like I said, I will look at ways to come up with some sort of way to do a definition quiz. If I do, it's going to be likely something like a repeatable quiz. But I'll let you know about that if I come up with something that works. All right, in any event, this is your second video. Feel free to watch it as many times as you want. I will have more up by the end of the week. And if you have any questions, contact me on Google Hangouts or email. And I look forward to working with all of you. Have a good night and have a good semester.